Whoa, here's the start of the chapter on solutions, and let me start by asking you a question. Will drinking ocean water quench your thirst? And if you haven't, you probably know the answer is. The answer is no. Ocean water tends to be about 3.5% salt, mostly sodium chloride, and our body, or at least our cytoplasm and blood plasma, are about 0.9% salt. So, short answer is no, it won't. There are some sea creatures like sea otters. They can really good kidneys and they can quench their thirst by drinking sea water. But we humans, we cannot. What happens when you inject distilled body or water into your body? Well, uh, it's actually a bad thing. You can get your red blood cells might explode because if you have different concentration of salt in the inside and the outside. So on the left here, there's normal red blood cells. If you inject distilled water into your bloodstream, what happens is that the water will rush into the red blood cells and might explode them. If you have too much salt in your body, what can happen is the water will leave your red blood cells and they get shriveled up in the middle. So this chapter is about solutions. Should probably start by talking about what a solution is. A solution is a homogeneous mixture, so a uniform mixture of two or more pure substances. So ocean water, for instance, is 96.5% water and 3.5% salts, mostly sodium chloride. There's other salts in there. And some terminology, solvent is whatever is the most of it. It's what does the dissolving. The solute, that's the least amount that is what's being dissolved. So here, most solutions, most of them we think of as liquid solutions, but there's other types. So there's gas solutions, so gas and air. Air is a solution. It's mostly oxygen, nitrogen, a little bit of argon, and trace other gases. There's also gases dissolved in liquids, so something like soda. So club soda is carbon dioxide dissolved in water. You can have two different liquids, so like vodka, ethanol and water, that's a solution. And you have solid dissolved in a liquid, so something like seawater. You can also get solid solutions, so alloyed metals, so brass, also gold. Gold is typically not pure gold, it's usually an alloy. So we have different types of gold, 14 karat, 10 karat. They're just different amounts of gold, silver, and copper. To illustrate this further, let me talk about a legal solution, and it's alcoholic beverages. So, for instance, beer here depends on the beer. The beer, I'll say that's 6% alcohol, depends on the beer, of course. Now, it will say it's just alcohol and water. What's the solvent? Water is a solvent, alcohol is a solute. Wine depends on the wine, of course, but 13% alcohol, 87% water. Water is still the solvent. Vodka. Depends on the vodka. Most vodkas are 80 proof. 80 just means double the alcohol concentration. And it's vodka typically is 60% water, 40% alcohol. So when people say you're drinking pure alcohol, you're still not. You know, you're still mostly drinking water. It's not a very good way to hydrate yourself, though. So then there's absinthe. Depends on the absinthe, but some of them is 70% alcohol, 30% water. Now we have a change. Alcohol is now the solvent and grain alcohol is 95% alcohol, 5% water, and now alcohol is the solvent again, or alcohol is the solvent again. So hopefully that example illustrates to you solvent and solute. We don't talk about this until later on the semester, but one of the reasons why solutions form is because of entropy. Entropy is a measure of disorder, and generally speaking, entropy increases throughout the universe. So one of the reasons why a solution forms, or one of the large reasons, is because of entropy. The entropy increases for the solution. And entropy has a couple definitions. One of them is the reversible heat transfer over temperature. Another one is R, the gas law constant, times the temperature, natural log of the number of microstates, or in the microscopic world, the Boltzmann constant times the temperature times the natural log of the microstates. So we'll talk a little bit more about later. But natural log of 1 is 0. That's the third law of thermodynamics, that the entropy of a perfect crystal at 0 Kelvin is 0. There's only one state. So we'll talk about this more later. And so like if you have two solutions, and this is the gas, neon, and argon, If you open up the gases, they'll mix and form a solution because it's more energy favorable. It is energy favorable, and it's also entropy wise. It's energy favorable because of entropy, and we'll talk more about that later. So we already mentioned intermolecular forces. You can see my previous lectures for much more detail, but everything has dispersion forces. There's also dipole-dipole and a special type called hydrogen bond, and then ion-dipole, the strongest. The strength goes from left to right. And solutions form in part because energetics. So if the solvent-solute interactions are greater than the solvent and solute-solute interactions, the solution is going to form. So if there's a greater attraction between them, the solution forms. And if they're about the same, the solution will form as well because it's entropy driven. If the solvent-solute interactions are smaller than the solvent-solvent and solute-solute interactions, the solution may or may not form. It depends on a couple things, if it's energy favorable or not. And that comes from Gibbs free energy, which we'll talk about later. The Gibbs free energy is the change in enthalpy minus, although the change in Gibbs energy is the change in enthalpy minus temperature times the change in entropy. And we'll talk about this much more in detail. But if the entropy change is strong enough with the temperature, even though if it's an endothermic process by delta H, the process will work. So another rule, this is a general rule, like dissolves like, meaning polar will dissolve polar, and also some ionic compounds. Nonpolar will mix with nonpolar, but polar tends not to mix with nonpolar, and it's because actually the polar compounds do not like the nonpolar. They get in their way. When polar compounds form a solution, there's an attractiveness. And the electron clouds in the nonpolar substance, they really like the polar molecules because the positive end of the molecule. So the electron clouds favor in the nonpolar, they favor the polar molecules. But typically what happens is the polar molecules push the nonpolar out of the way. So a lot of people say like oil hates gasoline, or I'm sorry, oil hates water, or gasoline hates water because you put it on water and it just splits it right up. Actually, gasoline loves water. It would much rather be with water than the gasoline, but the gasoline gets in the way of the water network, and then the water pushes it out of the way, and then it floats due to gravity, just on gravity. Okay, solubility. So what with his like dissolves like rule. And part of this is vitamin solubility. So there's some vitamins we need every day. So let's back up. What is a vitamin? A vitamin is a nutrient that we need in small amounts. So we humans have very large macronutrients. I mean, obviously we need lots of oxygen, we need lots of water. So we need those in pretty large quantities. We also need fats, carbohydrates, and proteins in relatively large amounts. And we also have minerals. Minerals are elements we need in small amounts. And then we have vitamins. Vitamins are organic molecules, are carbon-containing molecules. That's what organic means, carbon-containing molecules that we need in small amounts. And so some of these we need every day, some of these we don't need every day. So let's look at vitamin C here. And something to note about vitamin C, there's lots of OH groups on this. And vitamin C actually is water soluble. So vitamin C our body will not store, and it's water soluble, so we need to get a vitamin C every day. And we actually need 60 milligrams of vitamin C every day. If we don't get 60 milligrams, we will get a condition called scurvy. And vitamin C, the name of vitamin C is ascorbic acid. It's anti-scurvy acid. It's an acid, and it's anti-scurvy acid or ascorbic acid. And it's very, very hard to overdose on vitamin C because it's water soluble. We will renally excrete what we don't need. That doesn't mean that megadoses are favorable. Vitamin C is a reactive molecule, and it's an antioxidant. So what is an antioxidant? It's a reducing agent. So what vitamin C does is it protects, it's our primary antioxidant. It protects our bodies from attack from other molecules. So imagine I have a plate full of Brussels sprouts. So let's say I've got a huge plate of Brussels sprouts, and then there's a bunch of grade school kids that are going to come in, they're all hungry, and I don't want them to eat my Brussels sprouts. how do I prevent those kids from eating my Brussels sprouts? I'm going to put a bunch of Halloween candy in front of the Brussels sprouts, and the kids are going to go eat all the Halloween candy, and then they're going to be full, and they're not going to touch the Brussels sprouts. So how do I prevent my DNA and my cell from being attacked by a high energy free radical? Well, I have vitamin C there. So the high energy free radical is going to attack the vitamin C molecule. Vitamin C will be destroyed, but then my cell's DNA is going to be fine. So that's what antioxidants do, and many of the vitamins are antioxidants. So vitamin C is our primary one, a primary antioxidant. It's water soluble, and we need quite a bit of it. I mean, not as much as like fats or proteins or carbs, but I mean 60 milligrams a day. Some nutritionists say you need 200 milligrams a day. This is a debatable thing. Problem was with vitamins is that much of what we know about the vitamin is based off of deficiency diseases. So scurvy is a deficiency disease for vitamin C. And it's hard to say how much does your body actually need. The other thing is that so if you look at the certain units, they're unique for each vitamin. So there's no convention for the amount. Like it says, oh, this many units, international units of vitamin A. It's different for the unit in vitamin A is different for vitamin D, for instance. They don't translate to one another. So, okay, so vitamin C, water soluble. Then B, vitamin K3. And if you learn more about organic chemistry, you might see a ball and stick model. So, like here, I've drawn the two two dots and the lines coming together. You would know that each corner is a carbon atom, and then the whatever is not noted already has the hydrogens filled. So vitamin K can be written as the molecule I've drawn on the right. And vitamin K, you can see there's no place for a hydrogen bond. Therefore, vitamin K is fat soluble. So we store vitamin K. So vitamin K, this is something you tend not to find in the supplements. This is actually provitamin K3. This is something your body will turn into vitamin K. And I mean, there's lots of vitamin K in spinach, for instance, and other leafy greens. But your body turns it into the vitamin K. If you take a lot of vitamin K, you can actually die. Vitamin K K is for coagulation in German. And sorry about that. I had someone come in the door. Joys of teaching at home versus class. Anyway, so vitamin K, the deficiency disease for vitamin K is hemorrhage. You start to bleed out your eyes and ears and that kind of thing. So it's like be like a hemophiliac, for instance. And you actually can get this disease. We make our bodies. We have a symbiotic relationship with bacteria, such that we can make vitamin K ourselves. Well, it's symbiotic with our gut bacteria. And if you have a lot of antibiotics, you can break that symbiotic relationship, and you can become vitamin K deficient. Vitamin K is only available. Pure vitamin K is only available by prescription only, because it's a good way to kill yourself, either intentionally or accidentally. Taking too much vitamin K will turn your blood into a slurry. It'll be like cake batter, and the effect of too much vitamin K is your blood pressure drops very rapidly. But that's also what to do if a patient comes in that is hemorrhaging. They inject the patient with a large dose of vitamin K, and that prevents hopefully will stop the hemorrhage. So vitamin K, fat soluble. Here is vitamin A. Vitamin A has an OH group at the end, but the rest is all hydrocarbon. And it turns out vitamin A is fat soluble. Vitamin A is known as retinol, so retina, your eyes. The deficiency disease of lack of vitamin A is night blindness. We need vitamin A. Vitamin A is also an antioxidant when we use it in our eyes. So, and vitamin A is toxic in large doses. So apparently one of the best sources of vitamin A is a polar bear's liver. But polar bear liver is discarded by the Native Americans up in Alaska and in Canada. If they were to hunt polar bears, they would discard the liver, because consuming the liver of a polar bear will cause acute vitamin A toxicity and can result in death. But beta carotene is provitamin A. Provitamin is it's a molecule that our body can turn into the vitamin. Beta carotene is completely non-toxic. You can eat so much beta carotene that your fat turns yellow and your skin turns orange. It's non-toxic. So eat all the beta carotene you want. So if you're worried about vitamin A toxicity and you drink like carrot juice and it says like 5,000% of vitamin A, you're fine. You can drink carrot juice. It's not going to kill you. If it was polar bear liver, that will kill you. So provitamin versus vitamin. And here's vitamin B5. There's lots of different vitamin Bs. What vitamin Bs do, they generally help the operation of our energy systems and the way our nerves work. So it's kind of those two realms. And the deficiency disease, there's a bunch of different vitamin Bs. They cause different symptoms. So it depends on which vitamin B you are deficient in. And it has an OH group here, so an OH group here, NH group here, OH group here, OH group here. And this is in fact water soluble. So vitamin Bs are water soluble. So you can take we need vitamin Bs every day. So some caution though, just because we need them every day doesn't mean you want to overdose on them. So having too many vitamins, it's a moderation argument. So too little causes deficiency diseases, and too much can cause other problems. So it's some research has suggested that too much vitamin C can be a cause of cancer, for instance. So a very heavy antioxidant diet can cause cancer, but does that mean you should get rid of all antioxidants? No, you'll get scurvy, and you'll get night blindness from lack of vitamin A. So you need to have antioxidants, but you can't have too many of them. Same thing with vitamin B. Mega doses of vitamin B6 could eventually lead to nerve damage, especially in the lower extremities. So it just depends on the application. So okay, we've already mentioned vitamins A, B, and C. There's vitamin D, and that deals with how our bodies store calcium and magnesium in our bones. That's fat soluble, and we store that, and that's how people like me. I'm a very fair-skinned Caucasian, and some of my ancestors are from up in Northern Europe, and it gets dark for a bit there, so we can store the vitamin D's in our fat tissues and not get rickets. Rickets is the deficiency disease. We get really bendy bones from that. Mushrooms, though, are a good source. So milk is a source. Mushrooms is another good source of vitamin D. And vitamin E. Vitamin E is an antioxidant as well, but it's a fat-soluble antioxidant. But it's just like the general fat-soluble antioxidant. The deficiency disease kind of kind of similar to scurvy, but not exactly same as scurvy. Your skin kind of gets a little flaky and that kind of thing. I've never had any deficiency disease, so I don't know. Okay, so what do you think? This beta carotene. Here's beta carotene, and is this water soluble or fat soluble? It's fat soluble. I told you, kind of said before. Vitamin A. If vitamin A is fat soluble, this is a straight hydrocarbon. This is definitely fat soluble. And something to note, that there's this alternating single and double bond in that. When you see a molecule that has alternating single and double bonds, they are really colored and pretty molecules. And beta carotene is a reddish orange color. So, and a lot of the other molecules are like that. They're very colorful. So for this class, though, the amount of things you need to know about water soluble or fat soluble. If you see a bunch of hydrogen bond sites, then it's water soluble. Is there a certain number? Not really. Just if you see a lot in one, or if you see none, it's going to tend to be pretty obvious. You look at there, the vitamin B5, and then the vitamin C. There are 4 sites here. Not only that, it's not a direct carboxylic acid group, but it's you have quite a few in the molecule, or something like vitamin K, there's none. It's not so fair to see, vitamin A does have the OH on it. Just because something has an OH on it doesn't mean that it's going to be water soluble, though. Cholesterol Cholesterol it's an alcohol. Alcohol means OH, and it's a steroidal alcohol, and it's not water soluble. Okay, what about this molecule? Do you think this molecule is water soluble or fat soluble? It does have the one group right here for hydrogen bond, but in generally speaking, this molecule is fat soluble, and this molecule is known as lysergic acid diethylamide, also more commonly known as LSD. So this molecule, it's fat soluble. So if you were to take this molecule, your body can store it, and there are certain types of drugs that uh, that can stick around your body for a while. Also, if sometimes when fats are burned, you can get a larger dose of this back in your system. PCP has been known to do that, and some of the cannabinoids like THC. THC is lipophilic. It's fat soluble. Lipophilic. That's fat loving lipophilic. And THC users, chronic THC users, have reported a phenomenon known as reverse tolerance. So, for instance, generally speaking, if you take drugs, you tend to get a tolerance to them. Some heavy users of marijuana report reverse tolerances where they have to use less and less of the product to get a high. That's because it's still being stored in the body. It would be alcohol is water soluble, and you can build a tolerance for alcohol, but if you get drunk off of 3 beers and then you become sober, and then you drink another beer and you're drunk again, like, I have a reverse tolerance. Like, no, the alcohol just hasn't left your system yet. So that's same idea with the reverse tolerance with that. And there are certain molecules that are, and we mentioned the alcohols like cholesterol and retinol. Let's look at some of the molecules here. Methanol. Methanol is miscible in water. So it's the solubility in water. Miscible means it's in infinite quantities. And alcohol just means it means a hydrocarbon attached to an OH group. And methanol, also known as wood alcohol, is not terribly soluble in hexane. But ethyl alcohol, so ethanol is stuff that's in alcoholic beverages. It's unique because it's soluble in both water and in hexane, so in gasoline. So that's why and it's infinitely soluble. You can put alcohol at any concentration of gasoline. So it's an interesting molecule, alcohol, ethyl alcohol is. It's water soluble and it's fat soluble. Our bodies, we excrete it pretty quickly. Propanol is the next one down, so 3 carbons. Ethanol is 2 carbons. Methanol is 1 carbon. Ethanol is 2 carbon. Propanol is 3 carbons. And propanol, you're probably more interested in isopropanol. That's this propanol here has the OH at the end. Isopropanol, also known as rubbing alcohol, that has the OH in the middle carbon. And these are also infinitely miscible in both water and in most nonpolar substances. Butanol here is 4 carbons. Butanol, we're looking at butanol as perhaps a fuel replacement for gasoline. So it's suggested to use ethanol or methanol for gasoline. So an issue is not so much in Hawaii, but on the mainland. If you drive across the nation, you'll notice that there's an exit about every 30 miles or so, and that's because most cars can go about 30 miles in a gallon. And so if your fuel light goes off in your car, you should be able to make it to the next gas station. Methanol has about 44% the energy of gasoline, which means if you can go 200 miles on a tank of gas, you can go 88 miles on a tank of methanol. And so methanol is not a very viable fuel. It's also really toxic. Ethanol, if you use ethanol is 2/3 the energy. So if you can go 200 miles, that means you can go about 132 miles on a tank of ethanol. And the ethanol is a little harder because it's really hard. It's pretty reactive. It's not as gasoline is very unreactive. It's also jam-packed full of energy. Ethanol tends to dissolve things. It's hard to transport. as well. And so cars that are E85, any car will run off of ethanol. The tubes, the fuel line tubes are different for ethanol, and also same thing with the biodiesel. It's the engines are the same. It's just the tubing is different. That's what makes it special. And if you put E85 ethanol in a car that's not flex fueled ready, you will clog the fuel filter and the car will stop. So butanol, though, we're looking at butanol because it has about 80% or so the energy density of gasoline, and it's not as reactive as ethanol is. So we're looking at that as an alternative fuel in the future. So, but now as I'm recording this, gasoline is still king. Okay, so that's it for this lesson. I will see you for the next one.